So I'm really happy to be able to speak with you today and share some work that has been done with one of my PhD students, UT Cal, at Imperial College, where I'm based. So this is a talk on topological data analysis, which is one of my main fields of research. Okay. The context is in persistent homology, which is considered to be sort of one of the main workhorses of topological data analysis, and certainly the most popular tool that's been really widely used in many, many applications up until now. So essentially, it's adapting some theory from algebraic topology, and the idea here is to sort of quantify your data, right? And these data here can be very complex and have an unstructured nature. So they can be point clouds, they can be networks, they can be images, they can be surfaces, they can be almost anything. And the idea is that you quantify your data and capture some aspects pertaining to its size and shape. So in this talk in particular, all of the results are going to be focused on the particular filtration, like the particular version of Vietoris-Rips persistent homology. And so I'm going to present there like the sort of specifics of what we're talking about. So the idea is to basically look at the Vietoris-Rips filtrations. So, right, so for filtrations, essentially what we have is we have finite metric spaces here, and we're going to build some kind of nested sequence. So the construction of persistent homology always starts with a filtration, which is a nested sequence of topological spaces. And here in the Vietoris-Rips filtration, what we're looking at is an increasing sequence of parameters, our epsilons, so 1 through n. And at each parameter value, epsilon I, we're computing the VR, so Vietoris-Rips complex, by adding a node and a k-simplex for each collection of nodes that are closer together than our parameter value epsilon I. So here, epsilon I, we can really think about it as a kind of a radius, right? So since the epsilon I's are increasing in value, we get a VR filtration as a nested sequence of these VR complexes. So so basically the sequence of inclusions, so the sequence of inclusions, right, it induces maps in homology for any fixed dimension, and for each VR complex here, we take the homology group with coefficients in a field, and then this gives basically a sequence of vector spaces. So this collection of vector spaces together with the vector space homomorphisms is called a persistence module. And so basically notice that this definition is very kind of like algebraic, it's algebraic topology, but essentially since we have this sort of filtration and we have this very sort of geometric construction with these VR complexes associated with it, it can actually also be viewed as integral geometry. So, there are sort of like topological concepts being captured here, but also geometric ones. Okay. So essentially, like we have these, okay, so we basically have these persistence modules now, and then there's a structure theorem which says that you can decompose these persistence module into rank 1 submens, which correspond to birth and death times of homology classes as we sort of go through the filtration with the increasing sequence of radii here. And so once you have these sort of birth and death times, then what you do is you plot the collection on a persistence diagram. So you take each birth and death pair as an ordered pair, and then you can sort of scatter these and you'll get a persistence diagram, right? So essentially what this is that it's a locally finite multi-set of points. And then for technical reasons, we also have to include the diagonal, right? So the diagonal here is like the value where features are sort of born and die at exactly the same time. And these are counted with infinite multiplicity. Okay. So this is the idea of persistent homology. It's useful and interesting. It's been used in many applications by now in many different fields. So it's useful, it's interesting, but it's very expensive to compute. So the standard algorithm, which was originally proposed by So Morodian and Carlson to compute persistent homology has qubit complexity in the number of simplices. So this is quite expensive. There's been lots of sort of developments and work since then, including recent work, which basically look for algorithms to get something faster, right? So we have a slight improvement. The best complexity value has been reduced from 3 to 2.376 in 2011. But it's still very expensive to compute. And also, like, with this nature that we have of this kind of like filtration, right, where we have a kind of increasing nested sequence here, it really makes the idea by philosophy not parallelizable, right? So it's this is one of the things that's a major limitation in using persistent homology on very, very big data sets that a lot of people care about these days. So the question that Yuji and I asked is, because we deal with very big data sets quite a lot in the applied work that I do, and so what our question is, what can we do when our data set is just simply too big to compute persistent homology, right? And this happens quite a lot. So here we look at sort of more statistical ideas, right? So in 1979, Bradley Efron introduced the notion of bootstrapping, which is an extremely powerful and since then has become an incredibly popular inference method. So I'll talk more about that later, but just so for completeness, this idea of bootstrapping, which is this idea of multiple subsampling from your data, it's already been used in TDA in a couple of instances. So here are some work that have studied this notion of bootstrapping, but it hasn't ever been for the specific problem of basically doing persistent homology computations when our data are just too big. So I'm going to start now with the sort of punchline of the talk, right? So if you care about, like, if you want to run away and go do something else, right? So here's really the punchline of the talk, right? So what can we do when our data set is too big to compute persistent homology? Well, the mean of persistence diagrams computed from multiple subsamples, right? So, or bootstrap samples drawn from this massive data set is a good approximation of the true persistence diagram of the massive data set, right? So you have this huge data set. You can't compute persistent homology on the whole thing. But if you randomly draw with replacement random subsamples, and then compute the persistence diagram for each of these smaller subsamples, and then take the mean of all of these persistence diagrams, then this is a good approximation, right? And you can use this for your to basically approximate the persistence diagram of the huge data set if you were able to compute it. Okay. There's been work done on approximating persistent homology, which I'll also briefly touch on. Basically, there's one work by Shazal and collaborators where they focus on taking one sample only, right? So we're taking multiple samples, but this work has looked at taking one particular sample. And then there's been some work by Yasu Hiraoka as well, where they establish strong law of large numbers for persistence diagrams, but not in the bootstrapping context. Okay, so here's the punchline of the talk, right? So, but there are some technical questions here, right? Because this idea is kind of very nice, it seems very natural, but the idea is like, okay, there are some still sort of fundamental technical questions here to address. So the mean of persistence diagrams is one thing, right? Like what is the mean? How do we compute a mean of these quite algebraic objects, right? Multiple subsamples. So we want to draw multiple smaller subsamples. So how many subsamples is enough? And how big do these subsamples have to be? And then finally, good approximation. So, okay, we're approximating, right? But how do we measure our approximation? Okay, and how do we determine whether it's good or not, right? So these are like the technical things that I'm going into next. Yeah, that's what I'm going to answer now. So, okay, the first question is, what is the mean of persistent homology? Well, the first proposal of a mean of persistence diagrams relies on a very natural statistical generalization. of a mean. So this is the Frechet mean. So it generalizes the usual arithmetic mean that we all sort of know and love from, you know, very, very kind of like the most elementary things that we study almost all the time, right? To arbitrary metric spaces, right? So this here is a very metric geometric construction of the mean in general metric spaces. And what it does is it basically takes it looks to minimize the sum of squared distances between our candidate mean point and every single observation that we see. So this is what a generalized mean for metric spaces is. In the space of persistence diagrams, there are several metrics that we can work with. So this is this is a good idea. It's a good approach to looking for a mean. So one of the more natural metrics that we can use is what's known as the P-Wasserstein distance, which is given by this expression here. So moreover, what we know is that the space of persistence diagrams equipped with this particular metric here is a Polish space, which means that it's a complete separable metrizable space, right? So these are all the things that we need to do probability and statistics for it all to be sort of well defined. So it's a rigorous, probability and statistical space where we can actually ask all of these questions and statistics make sense. And then Turner, Kate Turner, who was the first person to look at this proposal of Frechet means based on this Wasserstein distance as a generalization of the mean for persistence diagrams, also proposed a greedy algorithm to find the local minima, because remember, the Frechet mean is an optimization problem in terms of a minimum. The problem with this, though, is that the algorithm is not well behaved. So first of all, there's non-convexity with the Frechet function, which is our objective function. So it's hard to find global minima. And also there's no rigorous initialization rule for the algorithm. So basically this means that different initializations can give different minima, which gives different values of the Frechet mean. And so it's not well behaved, but moreover, I mean, it's not just a limitation of the algorithm here, but there's also some results in the same paper about the geometry of the space equipped with the Wasserstein distance. So here it turns out that the space of persistence diagrams with this metric here is extremely highly positively curved. So this means that the geodesics are not unique. They're not even locally unique, which basically means that barycenters are also not going to be unique. So even though there's been sort of more recent work by Theo Lacombe, which try to sort of like update this algorithm and try to overcome some of the limitations of the algorithm, there's like the fundamental geometry of the space, which makes it very difficult to study these Frechet means. So yeah, so even though it's sort of a natural idea, there are some sort of limitations and caveats to be aware of when you're studying Frechet means, but nevertheless, it is a well-defined, honest to goodness, version, proposal for a Frechet mean, right? Yeah, so that's one idea of what we can say when we say, okay, means of persistence diagrams, right? So there's another one that's been proposed more recently, but before I sort of define what these persistence, this other sort of alternative mean is, so I'm just going to back up a little and talk about persistence measures. So this is more recent from 2019, where you can look at persistence measures as a sum, right, of measures essentially, right? So you have a sum of these sort of radon measures on your plane, right? And then what you do is that you basically look at the projection of each persistence point onto the diagonal, and you can look at the p total persistence of these ideas of these projections, right? And then you take all the radon measures, and then basically any radon measure here with finite persistence is called a persistence measure. This space here is a generalization of the space of persistence diagrams. So you don't actually have this multi-set of points anymore. You basically have this collection of measures here, but it is a generalization of a persistence diagram. It can be equipped with a distance also. So here they study this optimal partial transport distance, which is inspired from optimal transport theory. And then, there have been sort of properties studied about this, that it is a Polish space, which means that statistics and probability are, again, well defined. And also the fact that we have that the space of persistence diagrams is fully contained within the space of persistence measures, and that on the subset of the space of persistence measures corresponding to persistence diagrams, this optimal partial transport distance coincides directly with the Wasserstein distance we studied before, like we talked about before in the case of the Frechet means. This is really a proper, complete generalization in pretty much every sense of the word, in every sense that you would like, of persistence diagrams, right? So this is a proper representation of persistence diagrams as well, right? So here there are nicer statistical properties corresponding to these persistence measures, even though we don't have the same kind of nice interpretation of birth and death times with the actual points that we see on persistence diagrams, right? So here we can actually use this construction to answer the question, what is the mean of persistent homology? And you can do this by computing these mean persistence measures. So this is done in a very kind of natural way, right? I mean, this is really defined like in sort of classical statistics, where we define the expectation of, our random, our persistence measure valued random variable with a probability distribution, right? So this is, really like in a very kind of familiar probabilistic definition of expectation. But there is a nice sort of technology behind all of this, which relies on random, like theories of random measures and Bochner integrals, which bypasses the problems of computing these means that we saw in the case of the Frechet means, right? So here, essentially, with all of this theory that was kind of like, found in the literature from Devol and Lacombe, and so who proposed these persistence measures and these mean persistence measures and study the statistical properties of that, it turns out that here we have a well-defined Bochner integral, which is directly computable, and we don't have any sort of algorithmic limitations in the same sense that we saw with the Frechet means, right? So there's kind of like a bit more of a kind of complicated theory with all of this stuff of integration theory, which maybe is a bit kind of foreign to people who usually study topological data analysis and applied topology. But at the end of the day, what we get is we have a very, very nice kind of computable integral for this expectation. So this is a kind of really kind of a conceptual advantage of looking at these mean persistence measures over the Frechet means. But nevertheless, as far as the technical question goes, is what is the mean of persistent homology? We have two proposals here, which are well defined and make sense statistically speaking. Okay. So the next question now is this idea about samples, right? So like how many samples are good enough and how big do they have to be? So I'm going to sort of like show you some work, so here's some ideas that we're going to borrow from the one sample case, right? So some previous work done by Fred Chazal and his collaborators. They study this problem, the same problem that we do, where they're trying to sort of understand how well the persistence diagram of one subsample drawn from your larger sample approximates the persistent homology of your true metric space, right? So it turns out that the persistence diagram of this one sample, it approximates the persistence diagram of your larger point cloud at this rate here, right? So here, what you'll notice is that this approximation here depends only on size n, so that's the size of the subsample that you're taking, right? And then this sort of parameter b here, right? So this parameter b it basically comes from this idea of this A-B standard assumption. So A-B R naught standard assumption. So this here is basically used a lot in kind of probability theory. And essentially what it does is that it's a condition which makes sure that your probability measures are not singular, right? So it's basically, it prevents them from being too singular. So intuitively, the idea here is that, you have a volume or probability of some metric ball, right? And it should grow something like a b-dimensional Euclidean ball. So this is the idea, to sort of make sure that we have sort of well-defined probability measures in this case here. So basically, it's also it's something that is more from a sort of continuous case, but when we care about like computations and approximations, right, then we can also generalize this idea to include discrete measures on finite metric spaces. So this has been used before, and this is what we need here, because we're studying the case of finite metric spaces, because remember, the thing that we care about is a massive data set, right? It's a massive data set that is too big to compute persistent homology on, but nevertheless, it's a massive data set that is still finite, right? So we're still in the case of basically finite metric spaces here. So so this is what's known already in the case of one sample. It basically boils down to computing this convergence rate based on the sample size alone, and some parameter associated with making sure that your probability measures, which affects your sampling, is sort of well behaved. Okay, so all right, so that was the case for one sample, right? So then after that, the natural question is like, okay, but you can take many samples, right? So Fred Chazal and his collaborators, right, they did extend this work here to look at taking multiple subsamples here. But here in this case, instead of looking at persistent homology directly, or persistence diagrams, which is what we care about, they looked instead at this idea of a persistence landscape. So a persistence landscape was developed several years ago now, and it's a very popular vectorization tool. So what it is that it takes these persistence diagrams, which remember, they're these like scatterings of points, right, which are not vectors essentially. So it makes it very difficult to like integrate them into statistics, like, statistical methodology, classical statistic methodology, and most machine learning algorithms where you're normally dealing with vectors, right? So these landscapes basically are vectorizations of these persistence diagrams, and they give functional representations on R. The problem with these is that they're difficult to interpret it in the same way as you have with persistence diagrams. So you don't retain the same information of each point corresponding to a birth-death pair. But it is nevertheless a nice vectorization with good properties, but so this is something that is sort of like give and take. But these are the objects that was studied in the multiple subsampling case by Fred Chazal and his collaborators here. So the advantage of the computations that they're doing and using these landscapes is that now we have something that's linear. They're working in a linear space as opposed to the space of persistence diagrams, which is nonlinear. And then in this case here, they sort of look at the bootstrapping approach proposed by Efron, and come up with these kinds of results, right? So the idea is like looking at these landscapes, computing the means, as we are interested in, and then deriving some convergence results. Okay, so all right, so that's what's been done so far. And then the question that I wanted to ask next was about what's the approximation error, right? So here, how do we measure what we compute, what is computable versus the true value that we care about, right? So essentially, like the approximation error, the idea is to minimize the expected difference between the mean persistence measures, right, or the mean the mean representation of your persistence diagram computed from subsamples, and then the true persistence diagram of the massive point cloud that we have here. So this is a sort of standard expression taken from statistics, and then using the triangle inequality, we can decompose this expression into something that is basically the sum of a bias and a variance. So this is known as the bias variance decomposition for approximation errors in statistics. And so we can study these two quantities independently now to sort of get an idea of what the approximation error should be and how we can control this to make it small, right? Which basically means that, this representation that we have for persistence diagrams is going to be a good approximation of what we want, but we can't compute. Okay, so in the case of mean persistence measures, the variance has already been derived by Deville and Lacombe. They're the original authors who study these mean persistence measures. So we get as a corollary from their result an expression for what the variance looks like, and it looks like this. Okay, what about the bias now? Okay, so here this is going to take a bit more work, right? So again, we're working directly on the space of persistence diagrams or persistence measures here because we would really like to have this persistence diagram interpretation, right? We really want to have the persistence diagram representing this large, the persistent homology of the large data set that we can't compute, right? So here we're working in the nonlinear setting as opposed to the persistence landscapes setting before that Fred Chazal and his collaborators have looked at. So it makes it significantly more difficult, right? And what we want though is that we want some bound on the bias or some expression of the behavior of the bias, which depends only on our parameters, which are P, which correspond to the Wasserstein distance or the optimal partial transport distance parameter that we're looking at, N, which is the size of each subsample, capital B, which is the number of subsamples we draw, and then these A, B, R naught values that we were looking at before, which I mentioned about the controlling the size of the probability to make sure that the probability measures are not too singular. So if we want some expression that depends only on these, we have to basically apply two bounding procedures to move away from persistence measures to the setting of point clouds, right? So we can get expressions that depend only on this. So the way that we do this is we place a bound on first the optimal transport, partial transport metric, right? So this gives us something that reduces to the P Hausdorff distance. And then we place a bound on that P Hausdorff distance. And we do this by using some recently proposed techniques from just a couple of years ago by Deville and Lacombe, and also some more recent Wasserstein stability results by Primož Skraba and Kate Turner. And then we also use some random set theory to basically make sure that we get, the ABR not standard assumption part here. Okay, so let's do that. So the first step here, right, is that we have this inequality here. We have this sort of set of like inequalities. And what we do is we basically take results from Deville and Lacombe, where they establish a convexity result of this optimal partial transport metric. And it turns out that this optimal partial transport metric admits sort of a Jensen type inequality. And then if we look at the case of Dirac measures, in the case, which is basically what the case of persistence measures are defined by, we basically get the first inequality. And then the second inequality comes from this theorem established by Primož and Kate, which basically tells you that, if you have two finite sets in Euclidean space here, you can look at the persistence diagrams and the Wasserstein distance between these two persistence diagrams, and we can get a bound on that depending on some constant C, which depends only on N, which is the size of our the bound of the number of points in both of these sets, and the Hausdorff distance between them, essentially. Okay, so we have that now, and now we want to bound this Hausdorff distance, right? And so essentially we basically have this case where we can now take expectations, right, based on these optimal transport, the optimal partial transport distance and the Wasserstein stability that we've seen before. So here we adapt the same idea of what Fred Chazal and his collaborators did when they studied this problem in the case of persistence landscapes, to basically get some behavior on the covering number, right? So basically we adapt some idea of the covering number, some behavior of the covering number to basically get an estimate for the tail probabilities of the P Hausdorff bound, right? So essentially we adapt their lemma from the linear setting of persistence landscapes to our case of the nonlinear setting of mean persistence measures and persistence diagrams. And so we use this lemma here to get the bound on the second inequality here. So essentially this is quite kind of complicated and involved, and this is the first theorem from our paper that we can get. So it's basically it gives us this theorem here, tells us that we can get explicit bounds for the P Hausdorff distance for the bias only in terms of the parameters that we cared about, right? So here it's the P, small n and big N, right? So small n again corresponds to the subsample size, n corresponds to the size of the true data set that we care about, and then this A, B, R naught, which is the corresponding to the random set theory and probability restrictions to make sure that our measures are not too the So it's kind of a long and complicated proof, but basically it looks at the cases where we have different cases between the B, which is the radius of these Euclidean balls that we would like our probability measures to look like, with respect to the parameters of these metrics, and then integrating tail probabilities, right? So here we can get rate estimates for the approximation error, right? So we can sort of summarize these results together with the variance expression that we derived by basically following up on the variance computations that Divol and Lacombe did before. So here now we have basically this summary here of what the rate estimates should look like for the approximation error, right? So essentially what we can say here is that this is how the behavior looks like of our proposed mean persistence measure as an approximation for the true persistence diagram of the larger data set that we can't compute, and what it looks like and how fast it converges to the actual true value here. Okay, so basically some points to sort of like make about these rate estimates that we derived here. This is not the same thing as a kind of consistency result in classical statistics, right? So in classical statistics, one of the things that is often studied is this consistency property, which basically says that, like, okay, so how does this estimator or property that you're studying behave as n tends to infinity, right? So here in this case here, we're not looking at n tending to infinity because at the end of the day, we care only about this massive data set, which is too big to compute persistent homology on, but nevertheless a finite, very big data set, right? So here, this is a finite sample convergence analysis, right? So the fact that we have this finite sample convergence analysis has important, right, implications when n and b are both small, right? So basically when we're looking at, when we want to take only a small number of subsamples and we want each of these subsamples to be small, right? And this is in our interest because it basically makes the computation of persistent homology less expensive, right? Which was the whole problem in our case here of looking at persistent homology for a very, very big data set, right? So this has important implications because the case that we care about for computational efficiency is the part that actually precisely induces the randomness, right? So this is, despite it probably being, for methodological and mathematical statisticians, less interesting than the sort of classical convergence case when we have, our sample size growing to infinity. Here, this is where we still get randomness here, and this is actually one of the challenges in this finite sample convergence analysis that we derive here. Here also, we can also use these rate estimates to basically choose what B should be and what B, which is the number of subsamples we're taking, and how big these samples should be, because it's basically what we're doing is we're looking at this bias variance decomposition, right? And we look at the two values of the variance and the bias together, right? And then we want them to be sort of roughly the same rate, and we can actually use it to basically tune how big our samples and how many samples we should take should be. So this is how we can actually use our results also to tell you, like, okay, how many samples should we take and how big they should be. Okay, so this was all done in the case of the mean persistence measures. What about the Frechet means we talked about before, which is the first proposal for Frechet means? So we still have the same bias variance decomposition with this approximation error, right? We can still write this in terms of the value distance. The problem is that the non-uniqueness of the Frechet mean means that we can't get any expression for the variance, right? The only existing guarantee on the variance so far happens when Frechet means are unique, right? And so this is one of the lemmas that was proposed in the original Frechet means by Kate Turner and her collaborators. And again, it's for local minima only, not global. But crucially, it relies on this assumption that Frechet means are unique. But as we were saying before, right, we have this, very complicated metric geometry of the space, having it being very, very positively curved, which means that geodesics are, not unique, right? So it's very, it's far from obvious that Frechet means should be unique and that we can ever get, this kind of guarantee on the rate convergence here. So yeah, so this is the only thing that we have so far. It only holds when Frechet means are unique, which is far from obvious. So it's not something that we can actually even really kind of rely on. But we can still study the bias, right? So we did the same bias calculation as we did before. We can use this, right? But again, we can't get any kind of guarantees on how well a Frechet mean of persistence diagrams computed from subsamples would approximate the true persistence diagram for the larger data set. So here, we basically have the bias, but again, no rate estimates for the approximation error. Okay, so that's what we have theoretically, right? Let's see how this works in practice. So let's validate these convergence rates that we computed with some experiments. So here, this is just one experiment that we're taking that I'm showing here, although there are more in the paper. So we have the 2D torus, right? We consider the 2D torus to be sort of our underlying manifold, our finite metric space, right? We have 50,000 points from the torus, right? And we drawing samples here according to our proposed procedure. So here, if we're looking at values of p equals 3 and 8, we can actually compute what this optimal rate should be. It should look like something like that. And when we take samples, we see that, so red here is basically the true loss, which is sort of the approximation error that we're studying. And the blue is the theoretical curve that we compute. And then we basically sort of look at the dashed lines compared to the solid line, and we see that it's very close to our derived theory. So in practice, this also works. We also tested other types of data, right? So we looked at this in terms of Euclidean point clouds. So this is the setting that we derived all of our results on, but there are also other abstract finite metric spaces and networks, which we didn't derive any theoretical results on, but we were still thinking that, okay, what happens, how does this behave if we were to do it on other types of data as well? So it turns out that in terms of robustness and computability based on these other kinds of data sets that we looked at where we could actually compute this, our approach actually also worked quite well. So you can also apply our approach to this if you have like a large network, for example, that you'd like the persistence diagram for, and you can get something that works quite well, even though we can't give you any sort of theoretical guarantees on that. So that was also sort of nice to see in practice, despite lack of theoretical results. Okay, so the one thing that I mentioned before about these persistence measures, which is the only object that we have our that we have our theoretical results on is that they look like these kinds of fuzzy heat maps, right? Because remember, we're looking at radon measures, right? And we're not looking at persistence diagrams anymore, right? So persistence diagrams, they are these sort of scattering of points where we have each point with a very well-defined interpretable meaning, right? So each point corresponds to one homology feature, and when it was born and when it died. And once we sort of blur this into a kind of a radon measure heat map kind of thing, we lose this interpretation with the birth and deaths, right? But there is actually a way, if we study these persistence measures, to get back an interpretation of a persistence diagram where we have points and we can actually say again, this homology feature was born at this time and died at this time, right? So this approach is known as quantization, right? And this was more recently proposed by Fred Chazal and his students, where basically the idea is to sort of like have this kind of iterated process where you partition your persistence measure into Voronoi cells, look at the centroids of each of these Voronoi cells, and then take that as a persistence point, right? So in this case here, we'll have something approximate. It's not going to be exactly the same idea as a persistence diagram where we say each point is the true birth and death of this homology feature. Here we're going to have approximate birth and death times of the homology features, but it worked quite well. The code is very fast, and these papers here basically have guarantees on how well these quantizations of persistence measures give back persistence diagrams, right? Okay, so let's do this on real data now, right? So we're going to do this on this this image here, where we're looking at this digital shape workbench data set here, where we have a point cloud considering it corresponding to this object lock, right? So here n is 460,592 points. So this is too large to compute persistent homology on. And basically we're going to apply our approach, right? And see what we get here, right? So essentially, if you look at this original data, this is what the original point cloud looks like, right? So you can see here that basically we have some kind of inner tube and two caps on each side, right? So the underlying manifold, it basically looks like a connected sum of a torus and two surfaces of genus 4 each, right? So basically we have like a closed surface of genus 9 in the end. So 1, 2, 3, 4, 8 on, 8 holes on each side of these two caps on each side, and then we have one hole corresponding to the large one on the inner tube here. So the mean persistence measure looks like this. So this is what I was telling you before about these blurred kind of heat maps in the case of persistence measures. This is what the Frechet mean looks like. So here, again, we have this nice interpretation because this point here corresponds to the largest circle on the central tube of the lock, which is very, very difficult to see in this picture here, but essentially you have a very, very, very faint yellow point here, and essentially it's very, very difficult to get the same interpretation in terms of the holes that we're looking for from the persistence measure representation rather than the Frechet mean. But once we quantize, right, we get something that looks, reasonably close here to the Frechet mean here. Here, what we should have is basically we should have sort of 18 points, but we have some sort of noise corresponding to the filtration, the filtration procedure. But essentially what we see is we get something, so it works, right? So we can apply it to, this is a sort of like real data implementation is like, okay, if we were able to compute the persistence diagram for this thing, if we do it using the subsample approach, right, compute mean persistence measures or Frechet means, and then, or mean persistence measures together with quantization, this is what, our representative persistence diagram would look like. Okay, so this is a demonstration on real data. We've seen it already sort of guaranteed for synthetic data. This is the application to real data here. But how does this work if we wanted to do this and actually do some kind of machine learning task, right, or statistical task? So that's what we did next, right? So here we were taking the problem of shape classification, right? So again, we looked at this mechanical components benchmark, right, which is a collection of sort of 3D objects of mechanical components for 3D CAD, computer aided design. What we did was we looked at the bearing and motor from this database, and this gave us a total of 127 point clouds, right? So these are 127 representations of these two objects, bearing and motor. We have number of points for each of these point clouds ranging from 30,000, where persistent homology is still computable, to 250,000, where persistent homology is not computable. And we'd like to classify them into two clusters, right? We would like to classify these images as either bearing or motor. So we did that using our approach here. So we subsampled 15 sets corresponding to 2% of the number of points of the original point cloud. And then we computed the mutual optimal partial transport distance and used UMAP for dimensionality reduction, and then dbScan for clustering. And what we saw is like quite good behavior in terms of separation between bearing and motor here. So not only can you actually like do this, right? You can actually, our method, you can actually do it on real data, but if you actually needed to do it on real data and actually then do something else like a machine learning task, you can do this and it works, right? So yeah, basically just sort of wrapping up and giving you the big picture idea now, right? Like the kind of final take home message here is that if you have a massive point cloud that's too large to compute persistent homology, and you need a persistence diagram, then you can do this by drawing multiple subsamples of smaller sets, computing the persistent homology for each of these ones, and then either compute the Frechet means of these persistence diagrams or compute the mean persistence measures and quantize, and you get an approximation that's going to be a good approximation for the true persistence diagram of this massive point cloud. So there are no theoretical guarantees for the Frechet mean, right, because of the non-uniqueness of Frechet means, but there are theoretical guarantees for the mean persistence measure here, and we can tell you exactly how fast your subsampled approximation is going to reach the true value as well. Right, so some ideas for future research would be to derive the variance estimation for Frechet means. Of course, as I said before, this is challenging because of the non-uniqueness of Frechet means. But I mean, if you happen to be interested, like just a couple of months later after this work here, Yuichi also has another paper where he defines a geometric condition which guarantees that Frechet means are unique. But this is quite a kind of specific case here. But assuming that you actually have this, which is rare in the case of real data, then you can derive a variance estimation and also a similar kind of finite sample convergence analysis, which he did in his subsequent paper. So that's one direction of research, and something that has been partially answered now. Because we have this specific condition for uniqueness of Frechet means. More interestingly, what I think would be great is to sort of combine the mean persistence measures and the Frechet means to try and extract the positive traits of both of these approaches, to get some other kind of representation that you can use as a persistence diagram for your massive data set. So of course, here we're talking about in terms of positive traits of the mean persistence measures is the linearity of the space of these objects and the linearity of its corresponding space, which means that statistical computations are much easier. But the drawback is the fact that you have these kind of heat map like representations. Frechet means, on the other hand, you don't have sort of well-behaved theoretical guarantees, but you do have the nice interpretation exactly of what each of the persistence points mean. We would also like to study subsampling for other data types, right? So the ones that we actually studied here, like in our paper, which include networks and gene expression data and all these other things, which don't have a point cloud structure, because again, all of our results are dependent on a point cloud. So if you could derive kind of guarantees for network data, for example, that would be something interesting to look at. What happens if we subsample in continuous spaces, right? So here we assume that we have a finite metric space, but if we wanted to look at this problem of sort of the classical statistical problem that I mentioned before of like convergence analysis in infinite spaces, right? So here, this would be something very interesting to study. And then applications also to sort of machine learning. So like, for example, can you use a subsampling approach to sort of train neural networks, for example? That would be something interesting to look at. So yeah, there's code available if you want to use this. So, if you ever have a data set that's too big to compute persistent homology on and you want to use our approach, there's code available that you can download and use. I'd like to thank the PSRC and Imperial College for the President's Scholarship that funds UHC's PhD. This is also to sort of like point out, like also, just how talented and how fortunate I am to be working with UHC, because the President's Scholarship is extremely prestigious and awarded to only 50 students across the whole university every year. So I would say that like definitely keep an eye on UHC's name if you're interested in any of these sort of abstract computational mathematics and geometry kinds of ideas, because really interesting stuff is going to come from him. And then we also have some of the references for the main ideas that I talked about today, but of course, many other references in the original paper. So thank you very much also for listening, and happy to try to answer questions if you have any.